Now, to demonstrate how to use this formula, I switch to a simpler curve here. R of theta equals sine of theta. And I get this circle here in red, sitting just above the x-axis. And I'm going to calculate the arc length of this circle, starting at theta equals 0 and going up to a certain number. For right now, my upper bound is 1.5. And I can highlight that part of the curve in green here. So a little bit less than half of the circle. And remember my formula for the arc length. I'm integrating between my two values of theta. I've got r of theta squared plus r prime of theta squared. Now, for this example, Desmos isn't being so friendly about knowing what my functions are, so I'm going to have to manually put these things in. Since my r is equal to the sine function, I'll have sine squared of theta. And I can calculate the derivative of sine, no sweat, that's just cosine squared of theta. And now Desmos tells me that this integral is equal to exactly 1.5. Well, you probably noticed already for this problem, I've got sine squared of theta plus cosine squared of theta. Of course, that integrand is just going to be positive 1. Does it make sense that integrating this far should give me about 1.5? Well, if I look at all my theta values, it's a neat thing about this parameterization that if I look at values of theta between 0 and pi, ordinarily that would be half of the unit circle. But here I've completely enclosed the circle that I was looking at. And this says that my circumference, my arc length, should be exactly pi. Well, why is that? What is the radius of this circle? 0 and 1 are two different coordinates that are on opposite points here. So the diameter must be 1. Oh, that means that the radius is 1/2. So if my circumference is 2 times pi times the radius, and the radius is 1/2, then my circumference is just pi. Now, when we are working with arc length formulas, it's very easy to end up with an integral that does not have an easy antiderivative. And in those cases, it makes a bit more sense to rely on computer assistance. So when you're working in arc length, it's perfectly fine to do problems numerically, to ask a computer to run the approximations and find a value that's close enough for us, rather than working symbolically. We do want to encourage people to work via antiderivatives. So some of the problems on your homework will be with functions whose antiderivatives we can identify. So please try to find antiderivatives for those. But if you end up in a setting where you're being asked to calculate arc length for whatever reason that it's important to you, then the numerical approach, the calculator approach, might be more fruitful.